In this video, we're going to talk about the important notion of an inverse function. We'll talk about what it means for a function to have an inverse, and also how you can tell if a function has an inverse, or if a function is invertible. Take a minute to think about a standard telephone dial pad. Something you may not have appreciated before is that any dial pad has a natural function built into it. Indeed, each letter of the alphabet is associated with one of the digits 2 through 9, which has the effect of making it easy, for instance, to memorize certain phone numbers. All you need to do is memorize a certain word or string of letters, and then you can use the dial pad of your phone to output a corresponding string of numbers. So this is how the function built into your telephone dial pad works. The input is a string of letters, the output is a string of numbers. Now, let's try to turn things around and ask a related question. What if we start with a string of numbers and then try to use the dial pad of a phone to output a corresponding string of letters? Is it always possible to do that in a unique way? The answer this time turns out to be no. And the fundamental problem here is that whereas every letter is associated with just one digit, it is not true that each of the digits 2 through 9 is associated with just one letter. And this creates a certain kind of ambiguity. Let's consider another example. Suppose that at some moment of time, let's call it time t equals 0, a rocket lifts up off the ground and shoots straight up into space. Then a natural function associated with this situation would be the function that takes a given moment of time, let's call it t, and associates to it the altitude of the rocket at that moment of time, t. And here the input t will just be some moment of time in between liftoff and the moment when the rocket reaches space. Let's once again consider the question, what if we turn things around? What if we start with an altitude of the rocket and then ask the question, can we recover the moment in time at which the rocket attained that altitude? Is this a question that we can answer in a unique way? This time, the answer is yes. Indeed, as long as the rocket is moving straight up into space, then its graph would have to look something like the graph shown here. It would be an increasing curve that never backtracks or moves down. It would always be moving straight up as time progresses. And that means, if you think about it, that not only is it the case that for any given input t, there will be exactly one output a, it will also be true that for a given output a, there will be exactly one corresponding input t. And one final example before we move on to formalities. Let's say that you'd like to go for a jog along a closed loop that starts and ends at the same place. Then, during the time when you're running, we can associate to any moment of time your corresponding speed, which is an example of a function. But let's once again try to turn things around. Is it also the case that corresponding to a given speed that you are moving at, we can associate a unique moment in time at which you are running at that speed? Here the answer would be no. Indeed, your speed as a function of time might look something like the graph shown here. In any case, it would have to be a graph that starts at 0, because you start from a standstill, then increases and perhaps wobbles back and forth a bit before returning to 0 when you finish your run. And as long as that's the case, it will be true that for a given speed, some given output, there will have to correspond, in general, at least two different inputs, at least two different moments of time at which you are traveling at that speed. All three of the examples that we just considered are grappling with the question of when a given function can be inverted, or when a given function will have an inverse. So here is the general definition of an invertible function. We say that a function f from a to b is invertible if for any element y in the range of the function f, there is exactly one element in the domain of the function x, such that f of x equals y. Now, this definition may take a bit of time for you to fully wrap your mind around, but after you unpack it, try to see how it's really just a definition that kind of inverts the very definition of a function itself. An invertible function is one that does not only assign to every input exactly one output, it is also a function for which, for every output, there is exactly one input. Let's see how this definition plays out when we consider an abstract function diagram. We'll assume that we have two sets, A and B, on our hands, and that each of these sets contains exactly 3 elements. Here's an example of a function that is not invertible. Indeed, this diagram shows a function, right, because for every single input, there's exactly one output associated to it. But notice that there is an output in the set B that has 2 different inputs associated with it. This makes the function not invertible. On the other hand, here's a function from A to B that is invertible, because for every single output or element in the range of the function in B, there is exactly one corresponding input. A wonderful feature of invertible functions, which makes them so important, is that they can be undone to provide a new function, which, in this case, moves from the set B to the set A. This is the so-called inverse of the function f, and there's some special notation that goes hand in hand with it. And notice how, in our diagram, the inverse function is very easy to understand. It's obtained simply by reversing the arrows that define the function f. As we've seen, not every function is invertible, but if a function f is invertible, then it will have an inverse function, and that inverse function is denoted f to the minus 1. The way this is pronounced is simply f inverse. And please take note, the notation f inverse, which is written as f to the minus 1, does not mean f to the power minus 1. In particular, it does not mean 1 over f. It's very important to be careful about that distinction. Although the notation for an inverse function is inspired by the notation for the multiplicative inverse of a real number, it does not work the same way. There are many things to say about invertible functions, and also about the question of whether a given function is invertible. But let's try to start by analyzing things graphically or geometrically. Here, for instance, is the graph of a function, and we can see that it's the graph of a function because it passes the vertical line test. Any vertical line drawn in this graph will intersect the blue curve, the graph of our function, at most one point. So this is the graph of a function, but is it the graph of an invertible function? Well, to answer that question, we can use not the vertical line test, but the so-called horizontal line test. Indeed, notice that it's possible to draw a horizontal line through the graph of this function, which intersects the graph at more than one point. This tells us that this function is not invertible, because there exists a certain output, right, which corresponds to the height of this horizontal line, that corresponds to multiple different inputs. And an invertible function must be such that there is only one input corresponding to a given output. Geometrically speaking, an invertible function must pass the horizontal line test. Here's the graph of another function. Let's ask the question, is this function invertible? Well, by using the horizontal line test, we can see that any horizontal line drawn through the graph of this function will intersect the graph at most one place. Therefore, this function is invertible. At least the part of the graph that we see here is invertible. And this raises an interesting question, namely, as long as we know that this is the graph of an invertible function f, well, how can we graph the inverse function, f inverse? It turns out that this can be done in a very natural way. Let's take a point on the graph of the function f, and assume it has coordinates x, y. This means that the function f takes x as an input and gives us y as an output. And that in turn implies that the function f inverse will have to take y as an input and give us x as an output. In other words, the point with coordinates y, x will have to be a point on the graph of the inverse function. So the graph of f inverse will be obtained by taking all of the points on the graph of f and reversing their coordinates. Now let's think a little bit. Where in the coordinate plane will the point with coordinates y, x be? Well, it's going to be over here. And the reason the point is there is because if you take a point in the xy plane and reverse its coordinates, then all you do is reflect across the diagonal line y equals x. So geometrically speaking, reversing the coordinates of a point in the xy plane just means reflecting across the line y equals x. And therefore, to obtain the graph of the inverse of f, we would simply take the graph of f and reflect the entire graph across the line y equals x. The graph of f inverse therefore looks like the red curve shown here. And this actually gives us a general recipe for graphing inverse functions. To graph the inverse of an invertible function, just reflect across the diagonal y equals x. By the way, note that the reflection of a vertical line across the diagonal y equals x is actually just a horizontal line. This explains geometrically why an invertible function must pass both the vertical and horizontal line tests. Let's make one more observation about inverse functions in this video. We've seen that if a function f is invertible, and if it takes x to y, then the inverse function will have to take y to x. So follow the arrows in this diagram, and you'll see that the composition of a function with its own inverse will just have to give you the exact same input back. In particular, we have the important properties that f of f inverse of x will just equal x. And likewise, if we compose in the opposite order, f inverse of f of x will also have to equal just the input x. This gives us an important algebraic method for determining whether two functions are inverses of each other. Just compose the functions in any order and see if the resulting expression is equal to x. In this example, where we're being asked to determine whether the function f defined as the cube root of 1 plus x and the function g defined as x cubed minus 1 are inverses of each other, we can simply compute the composition f of g of x. That works out to be the cube root of 1 plus x cubed minus 1. Notice how we've just taken the expression that defines g and substituted into the variable x in the expression that defines f. And this simplifies to the cube root of x cubed, which is just equal to x. Therefore, the answer to the question posed in the example is yes, the function g is equal to the inverse of f. G equals f inverse.